All right. Hey, everyone. So today we're going to take a journey through sampling theory. We're going to start with this absolutely beautiful, elegant idea from engineering. And then we're going to see how that classic concept crashes right into a super modern problem that researchers are trying to solve right now. You know, at the core of everything we do in digital signal processing, it really comes down to this one big question. Think about it. The real world is continuous, right? It's infinitely detailed. And our job, our whole job, is to somehow cram all of that infinite detail into a nice, neat little stream of ones and zeros. So how on earth do you do that without losing everything that makes the signal special? Well, that's exactly what sampling theory is all about. But hey, before we can get to the solution, we've got to really appreciate the problem. And honestly, it's a fascinating one. See, when sampling goes wrong, it's not just a simple mistake. It's more like a deception. The signal can literally hide its true identity. It commits what I love to call the perfect crime. Okay, so what is sampling anyway? It's actually beautifully simple, which is what's so cool about it. All we're doing is taking little snapshots or measurements of an analog signal at these perfectly regular intervals. Tick, tick, tick. Each snapshot gets turned into a number, and boom, that stream of numbers is your new digital signal. It's the bridge that takes us from the analog world to the digital one. So take a look at this. This is what we're up against. This could be anything, right? A piece of music, someone talking. What I want you to notice are all those rapid changes, the little wiggles. That's the high-frequency content. That's the character of the signal. And our big challenge is, can we capture all of this with just a few snapshots and still be able to perfectly rebuild this exact same complex shape later on? And this is where the drama starts. What if our camera, our sampler, just isn't fast enough to catch all that detail? What happens if we don't take those snapshots frequently enough? Well, that's when we get aliasing, the perfect crime. A high-frequency part of our signal basically puts on a disguise and pretends to be a low-frequency signal. You've all seen this. It's just like when you see a video of a car's wheels spinning really fast, and suddenly it looks like it's spinning slowly, or even backward. The camera's frame rate, its sampling rate, is too slow and it's being tricked. And the worst part, once this happens, that's it. The original information is just gone. You can never get it back. So if sampling too slowly leads to this perfect crime, how do we stop it? Well, luckily for us, there's a beautifully simple, mathematically proven rule that acts as our master detective. It's the rule that ensures we always get our signal. And here it is, the big one, the Nyquist-Shannon sampling theorem. This is the bedrock of pretty much all of digital signal processing. It gives us this incredible ironclad guarantee. It says that as long as your signal has some highest frequency, we call that being band limited, you can capture it perfectly. All you have to do is sample more than twice as fast as that highest frequency. And that's the key, right there. Greater than 2 times. It's so important to remember, not equal to 2 times, but strictly greater. This rule of 2 is like the universal speed limit for going digital. You want to capture a 10 kilohertz tone? You better be sampling faster than 20 kilohertz. It's really that simple. And it's also that profound. Okay, so that's the textbook stuff. That's the theory. But what does this actually look like out in the real world? Let's check out a piece of technology that I'm pretty sure you've all used, that was built from the ground up on this one single principle. Let's talk about the good old compact disc. The engineers started with the limit of human hearing, which is roughly 20 kilohertz. So they just applied the Nyquist theorem. The sampling rate had to be greater than double that, so more than 40 kilohertz. They ultimately chose 44.1 kilohertz. Now, why the little extra margin? Well, that safety net is crucial. It gives the practical, real-world filters in the hardware some room to work without accidentally cutting into the music we actually want to hear. So for decades, we've understood this theory. We mastered it. We built the digital world on it. But a funny thing happened on the way to the future. While the theory is totally solved, trying to implement it at scale and in real time has created a completely new challenge, a modern bottleneck. See, in the past, if you wanted more processing power, you just made the processor's clock speed faster. Simple. But we've pretty much hit a brick wall with that approach because of heat and power. The new paradigm is parallel processing. So instead of one really fast brain, we now have multiple processor cores working at the same time. And this really captures our current situation perfectly. The math of sampling hasn't changed, but the hardware has, completely. The question for researchers is no longer what's the right sampling rate. The new question is,
How do we get all these parallel cores to perform our DSP tasks in real time without tripping over each other?
So, what are these new problems? Think of it like a team of cooks in a really busy kitchen. You need to manage the flow of ingredients, that's your data flow, with DMA controllers. You have to make sure no two cooks collide trying to use the same pan. That's avoiding memory access conflicts. And most critically, for something like real-time audio, you have to guarantee that the entire meal is ready at a precise moment. Ensuring all those parallel tasks finish on time every single time, that is the core challenge.
And this right here is where the textbook ends and where current research begins. And this is where you all come in. This isn't a solved problem, not by a long shot. It's an active area of research and development that you can absolutely contribute to.
If this sounds interesting, the best place to start is the literature. The IEEE Explore Digital Library is the premier database for this kind of research. So I'm going to give you a very specific search term to get you right to the heart of the matter. Search for this exact phrase. You'll find papers from just the last few years tackling exactly the challenges we just listed. This is how you go from a theorem from the 1940s to a really tough engineering problem in the 2020s. And that leaves us with this final question. The classic algorithms you're learning about were all designed for a single-threaded, step-by-step world, but our hardware now thinks in parallel. The critical challenge for your generation of engineers is to bridge that gap. How do we redesign our fundamental DSP building blocks for a multi-core world so that the elegant solution of the past doesn't become the bottleneck of the future? That's something I'll leave you to think about. Thank you for your time.